Today, let's talk about porphyrins. Um, I'm sure every one of you has ever heard of hemoglobin at one point of their life. And hemoglobin consists of heme and globin. Now, the heme part is a porphyrin. And in this session, we'll be looking at how is that heme part synthesized. Welcome all. My name is Horis Munyiri, and I'm the Daktari. Now, what are porphyrins? Now, porphyrins are cyclic compounds that usually bind metal ions, usually ferrous and ferric ion, mainly. Now, the most prevalent metal of porphyrin in humans is Heme, and it usually consists of one ferrous center, one ion in ferrous state in a coordinated, which is coordinated in the center of a tetrapyrrole ring of protoporphyrin IX, porphyrin 9. Now, Heme is usually the prosthetic group of some important compounds such as hemoglobin, myoglobin. Remember, we have some differences between hemoglobin and myoglobin, such as hemoglobin is a tetramer, myoglobin is a monomer. Hemoglobin has alpha and beta chains, with the alpha chain having 141 amino acids. Beta chains has 146 amino acids, but myoglobin is a single polypeptide with 153 amino acids. Now, also you have the cytochromes, they contain heme, and remember the cytochromes are very important, especially in the biotransformation of drugs. One example is the cytochrome P450. We also have some cytochromes in the electron transport chain. You have also catarase enzyme contains a heme, and catarase is very important in reducing reactive oxygen species. We also have nitric oxide synthase. Remember the nitric oxide synthase, the three of them, the neuronal one, the inducible one, and the endothelial one, 1, 2, 3. We also have peroxidase. Now, these heme proteins are rapidly synthesized and degraded, okay? For example, up to 7 grams of hemoglobin is synthesized every day to replace the heme lost through the normal turnover of the red blood cells, okay? Now, the synthesis and the degradation of the associated porphyrins and the recycling of the ion are coordinated with the turnover of these hemoproteins. Now, let's look at the structure of a porphyrin. They are cyclic planar molecules formed by linkage of 4 pyrrole rings through methynyl bridges. Now, let me take a pen and please note that in porphyrins, the pyrrole rings are usually linked by these bridges, the methynyl bridges. Unlike in a choline ring, remember the choline found in cobalamin, the pyrrole rings are linked directly. Okay, and here you can see now, like this one is a pyrrole ring, and this is the methynyl bridge, this one here. Okay, now the porphyrin which is of importance to us as in humans is the asymmetric porphyrins, the type 3 porphyrins. Okay, that one is the one which is of medical significance, as it is the one which we'll be looking at. Now, heme biosynthesis. Now, the major site for heme biosynthesis is the liver, okay? Where it usually synthesizes a number of heme proteins, particularly for the cytochrome proteins, and also the erythroid producing cells in the bone marrow, which are active in hemoglobin synthesis. Now, in the liver, the rate of heme synthesis is highly variable, okay? And it usually responds to alterations in the cellular heme pool caused by fluctuating demand for hemoproteins. Now, in contrast, heme synthesis in the erythroid producing cells, that is fairly constant, okay? And it is matched to the rate of globin synthesis. Now, over 85% of all heme synthesis occurs in the erythroid tissue, and mature red blood cells, note this, mature red blood cells usually lack mitochondria, and hence they are unable to synthesize heme. So the heme must be synthesized before those red blood cells exit the bone marrow. Now, the initial reaction and the last 3 steps, please note this, that the initial reaction and the last 3 steps in formation of porphyrins usually occur in the mitochondria. That is why matured blood cells cannot synthesize heme because they lack mitochondria. Whereas the intermediate steps usually occur in the cytosol. Now, let's have a look at that. I will not be reading this. Let's go directly to this diagram. We should start with glycine. Okay, take glycine, which is an unessential amino acid, and succinyl-CoA. Succinyl-CoA is an intermediate of the tricarboxylic acid cycle. And also remember, you can get succinyl-CoA from some amino acids, such as valine, yeah, also threonine. Also from odd-chained fatty acids, you can get succinyl-CoA via the methyl malonyl. Then the two of them are combined, a reaction catalyzed by the aminorevulinic acid synthase, okay? And there are two types. We have ALAS. ALAS is the abbreviation of aminorevulinic acid synthase. One is found in the liver or in all tissues, but mainly in the liver. ALAS2 is found in the erythroid producing cells, okay, in the erythroid tissue. Now, ALAS1 is the one which is now regulated by heme or the hemin, the oxidized form of heme, and ALAS2 is usually regulated by ion, okay? In this reaction, let me take the pen. In this reaction, we first remove a carbon. You can see a carbon dioxide is being removed, and this is where it comes from. And this CoA is also removed. Then we combine these two. You see, up to that part, upwards, that came from succinyl-CoA, and the other part came from glycine. Now, this is delta aminorevulinic acid, okay? Then, two molecules of delta aminorevulinic acid usually condense, okay? And that reaction is usually catalyzed by delta aminorevulinic acid dehydratase, and this is a cytosolic process. And one thing to note about this ALAD is aminorevulinic acid dehydratase, is that it contains zinc, and in lead poisoning, that zinc is usually replaced by lead, and this inhibits the enzyme, okay? Now, when two molecules of water are lost, then after condensation of two ARAS, you form porphyrinogen, okay? Now, note this, maybe I did not tell you this. How does heme or hemin inhibit ARAS? It can do that in three ways. Either one, it can replace the gene for transcribing ARAS1, or it can also increase the degradation of the messenger RNA for ARAS1, or since this, this is a protein, it is being synthesized by the ribosomes, but it acts in the mitochondria. We can also inhibit the importation of this enzyme into the mitochondria. So those are the three ways in which hemin usually inhibit ALAS. Okay. So next page. Now we had seen porphyrinogen formation. Then let's go to uroporphyrinogen. Now, for porphyrinogen combine to produce a linear tetrapyrrole known as hydroxymethylbilane, and that reaction is usually catalyzed by the hydroxymethylbilane synthase. Now, then it is a linear tetrapyrrole. Then we have to cyclize it, okay? It is usually cyclized and isomerized by uroporphyrinogen 3 synthase to produce the asymmetric uroporphyrinogen 3, okay? Then this uroporphyrinogen usually undergo decarboxylation, reaction catalyzed by the uroporphyrinogen 3 decarboxylase, urod. Please remember this enzyme because it is involved in one of the porphyrias. And after decarboxylating, we form coproporphyrinogen, okay? And up to there, all those reactions are occurring in the cytosol, okay? Let me show you that. I think here we are, porphyrinogen. Four molecules of porphyrinogen usually contains reaction catalyzed by the hydroxymethyl synthase to form hydroxymethylbutane. Now, hydroxymethylbutane undergoes cyclization and isomerization, a reaction catalyzed by the uroporphyrinogen 3 synthase to form uroporphyrinogen. Now, uroporphyrinogen 3 is decarboxylated, okay, by the uroporphyrinogen 3 decarboxylase, and please remember this enzyme, okay, to form coproporphyrinogen. Up to there, these reactions are occurring in the cytosol. Then coproporphyrinogen is taken to the mitochondria, where it is. That is why I've separated for you. These are cytosolic, these are mitochondria. Now, coproporphyrinogen 3 undergoes oxidation, a reaction catalyzed by the coproporphyrinogen 3 oxidase to form your protoporphyrinogen IX. Okay, then protoporphyrinogen IX will undergo further oxidation, a reaction catalyzed by the protoporphyrinogen IX oxidase to form now your protoporphyrin IX. Okay, now the last step is we have to add an ion. We have to add ion now to the protoporphyrin IX. Okay, you can see we are adding ion. Okay, and as we add ion, we remove these two hydrogens here. They are removed. A reaction catalyzed by the ferrochelatase. Okay, now ferrochelatase, just like aminorevulinic acid dehydratase was being inhibited by lead, also it is also inhibited by lead. Okay, so lead poisoning can inhibit heme synthesis at 2 points. Okay, after that we form ferrous protoporphyrin IX, which is now your heme. Okay, so I hope you are up to there. Now you have synthesized heme. Now let's look at some porphyrias. Now porphyrias are rare, inherited, or sometimes acquired defects in heme synthesis. Okay, and they usually result in accumulation and increased excretion of porphyrins or porphyrin precursors. Okay, now note that inherited porphyrias can either be autosomal dominant or autosomal recessive. Okay, now I will show you which ones are autosomal dominant and autosomal recessive. Now, each porphyria usually result in the accumulation of a unique pattern of intermediates caused by the deficiency of an enzyme in the heme synthetic pathway. Now, porphyria is derived from a Greek word purple, and usually refers to the red-blue color caused by pigment-like porphyrias in urine of some patients with defects in heme synthesis. Now, in general, please note this. Individuals who have enzyme defect prior to the synthesis of the tetrapyrrole. Now, if you have an enzyme defect before you form hydroxymethylbutane, remember hydroxymethylbutane is your first tetrapyrrole and it is a linear tetrapyrrole. Now, if you have an enzyme deficiency before we form hydroxymethylbutane, you will manifest abdominal and neuropsychiatric signs. You will not be photosensitive. But if you have enzyme defects after now we form the tetrapyrrole, that is after formation of hydroxymethylbutane, which will lead to the accumulation of the tetrapyrrole, the patient will show photosensitivity. Photosensitivity is where when exposed to light, they will have skin itches and a burning sensation. In quotes, and I say this is in quotes, it's like they are vampires. They cannot go to the sun. Okay. Now, this photosensitivity is due to the oxidation of the colorless porphyrinogens and to colored porphyrins, which are usually photosensitizing molecules, and they usually form superoxide radicals. And these radicals are cause oxidative damages to the membranes, and they cause release of the lysosomal enzymes, which now will lead to the photosensitivity. Now, here we are. Let's start here. The first, this is reaction number 1, and this is the last one here. Now, remember, this RS1 aminorevulinic acid synthase is inhibited by heme in form of hemine. Heme has a ferrous ion. Hemine has a ferric ion. It is the hemine which usually inhibit RS1. And I said it inhibits it in 3 ways. It can either repress the gene transcribinate or increase the degradation of the messenger RNA, which will translate the enzyme, or decrease the importation of the enzyme into the mitochondria. Then this aminorevulinic acid is transported out of the mitochondria into the cytosol, where two aminorevulinic acid condense to form porphyrinogen, and this reaction is catalyzed by the aminorevulinic acid dehydratase, which is inhibited by read. Okay. Now you see this is hydroxymethylbutane, the first tetrapyrrole. Okay. Now if you have any enzyme deficiency before we form the hydroxymethylbutane, you'd have abdominal and a neuropsychiatric sign, no photosensitivity now. But if you have a porphyria which occurs due to enzyme deficiency after the formation of this hydroxymethylbutane, you will have photosensitivity. Okay. And like this, you see the deficiency in this enzyme known as hydroxymethylbutane synthase. It is known as acute intermittent porphyria. Okay. And you see the urine will be dark on exposure to light and air, but you will not be photosensitive. Okay. But if you have deficiency of this enzyme here, uroporphyrinogen 3 synthase, you will have the congenital erythropoietic porphyria, but you'll be photosensitive. That is what I want you to note. But please, please, please remember this. Which enzyme catalyzes the conversion of uroporphyrinogen 3 to coproporphyrinogen? Uroporphyrinogen 3 decarboxylase. And deficiency in that enzyme results in the most common porphyria, which is known as Porphyria, CUTANEA, TADA. Okay, and it is the most common, and patients are photosensitive because the enzyme deficiency is after formation of the tetrapyrrole, and usually the uroporphyrin usually accumulates in urine. Okay, then these other ones you can look. But let me talk about this deficiency in ferrochelatase usually lead to erythropoietic porphyria. Now, these porphyrias are of two types. They can be either hepatic or erythropoietic. Hepatic in that it affects mainly the enzymes in the liver, erythropoietic in the erythropoietic tissue. And you can see we have two erythropoietic porphyrias, the congenital erythropoietic porphyria caused by deficiency of the uroporphyrinogen 3 synthase, and also the erythropoietic protoporphyria, okay, caused by deficiency in ferrochelatase. You can pause the video and look at this, the variegate porphyria and the hereditary coproporphyria. Okay. Now, we have formed heme. Will this heme remain in the body for the rest of your life? No, of course not. We need to degrade it. Now, after 120 days, about 4 months of circulation, the red blood cells are usually taken up and degraded by the mononuclear phagocyte system, particularly in the liver. Remember the Kupffer cells in the liver and the spleen. The spleen has macrophages in the splenic cords of B-lobe, and approximately 85% of the heme destined for degradation mainly comes from senescent red blood cells. The remainder coming from the other hemoproteins other than hemoglobin. The other hemoproteins, remember, like cytochrome, myoglobin, etc. Now, here we are. Here you can see the senescent red blood cell being taken up by a macrophage. Let's say this is a Kupffer cell in the liver. Then the heme is separated from the globin part. Then the heme is oxidized by the heme oxygenase. You can see you are putting in oxygen, NADPH, and hydrogen ion to give out NADPH. Then we are giving out this ion. And remember, this ion will be transported out of that macrophage via the ferroportin. Okay. Then via the action of a ceruloplasmin enzyme, it will be converted to the ferric form. Then two of them are bound to transferrin and transported to the cells which require the ion. Then you can see here, we have remember in heme, we have a protoporphyrin, which is cyclized, but here we open up that circle, that cyclic ring. We open it and it form a linear ring, not a linear ring, a ring cannot be ring. We like linearized it to form biliverdin. Okay, you can see the 4 tetrapyroles, 1, 2, 3, 4. Okay, then this biliverdin is a green pigment. It is usually reduced by the biliverdin reductase to form bilirubin, which I think is red brown. Okay, then after forming bilirubin, bilirubin is formed by the macrophages. Bilirubin is then conjugated with albumin. Okay, where it will be transported in the blood to the liver. Now, there are some drugs. I want you to go and find out which drugs usually inhibit the binding of bilirubin to albumin, especially anionic drugs such as, I think, sulfonylamides. Then bilirubin will undergo glucuronidation, conjugation. You can see here, put in 2-UDP glucuronic acid by a reaction catalyzed by the bilirubin UDP gluconosyl transferase to form bilirubin diglucuronide, your conjugated bilirubin, which is then excreted in bile. Now, I want you to go and find out jaundice. Jaundice, when reading about jaundice, know how we can divide jaundice. We can have of 3 types. It can be either prehepatic jaundice, hepatic jaundice, or posthepatic jaundice. Okay, prehepatic is maybe you have increased like hemolytic anemia, so there will be increased production of bilirubin such that it will exceed the conjugation, or it will be so much that albumin cannot conjugate it properly. Then hepatic, maybe you have a destruction of the liver cells, hence they cannot conjugate the bilirubin. Or posthepatic, maybe you have like a bile obstruction. Okay, so you cannot secrete this conjugated bilirubin into the digestive system. Okay, please go and look at jaundice. I think you've come to the end of that session, and please thank you for your attention, and please subscribe for more anatomy and biochemistry content. Thank you.